kind of cool. Okay, so now I'm adding the rest of the pieces into the filter. So I'm adding the inlet box, the inlet box, the outlet box, the filter box, this siphon pipe, and we're at the end of backwash. The operator has opened up this valve and left air into this pipe. And so there's this air that is trapped inside the high part of the siphon pipe. And the bed was just fluidized, and now it's going to stop, or it's going to quickly settle back down. And we're seeing some very interesting water levels in these pipes. I don't know if you see this, like water levels keep on changing inside each of these pipes. There's no flow in any of these pipes except for this first one, which is the backwash and bottom inlet. I don't know if you're making the connection that the rest of these pipes are acting kind of like manometers. They're a way of measuring what the pressure is in the filter at each of these different levels. And what they're showing is that the pressure inside the filter is dropping rapidly as you go up through the filter. So if we followed this more carefully, here's bottom inlet, next inlet, or next manometer, coming up the next manometer, coming up the next manometer, the next manometer, the next manometer, and the top manometer. These aren't really manometers, but they're acting like manometers right now. Manometers meaning the way to measure the pressure inside the filter based on how high the water level comes in each of those pipes. And what it's showing is the head loss through the sand bed, through the fluidized sand bed. Remember, there's a lot of head loss through the fluidized sand bed, and those manometers are showing that. Because remember, the water, during backwash, the water is going in up here, and when it leaves the filter, its elevation is way down here, and that difference in elevation is head loss through the sand bed primarily, and also through your inlet plumbing, the backwash pipe. That was that. That's the head loss through the sand bed and all the plumbing, both the inlet plumbing and the outlet plumbing through the siphon pipe. And what's this going to be? That is the depth of the sand. So this pi factor is the ratio of the backwash height of the sand divided by the height of the sand during filtration. And so that's the height of the sand during backwash. And I think that's that. Notice that these pipes here they have little pipe stubs on them, and those pipe stubs make it so that their inlet level is higher than what the water level is during backwash. So that makes each of these pipes be high and dry, and hence turned off because it's not even in the water when you're in backwash mode. If you didn't have these pipe stubs installed, can you see what would happen? If I didn't have those pipe stubs installed, then there wouldn't be any air in any of these pipes. And can you see what would happen? Remember, water wants to take the easiest path. And the easiest path would be to go in this top inlet, and actually at that point, the sand wouldn't be fluidized, it would just skip all the sand. Do you see this failure? If I don't have these pipe stubs, then when I think I'm going to start backwashing, instead, the water says, oh, I'll go in this pipe and I'll pop out right at the top of the sand, and I won't bother fluidizing any sand. So these little pipe stubs are absolutely critical so that water during backwash mode, when the water level is low in the inlet, can't get into any of the other inlets. It can only get into the inlet that we want it to go in, into the backwash inlet. Okay, so now we're going to go down this little side path of what's setting this change in height between these two pipes. What's that change in height from? So it's about head loss between those two trunks. And if we assume that the expansion ratio is 1.3, so that the height of the expanded bed divided by the height of the bed before it's expanded, the sand before it's expanded, is 1.3. Let's find the depth of sand. Let's begin by finding the depth of settled sand in 20 centimeters of expanded bed. Why am I doing this? Because I know that the head loss through the filter is, because of that funky relationship, is equal to 0.99, basically 1 times the height of the settled sand. So if I run water through 1 meter of settled sand and just put enough water through that so that it begins to fluidize, my head loss is going to be 1 meter. So I'm going to use that relationship to figure out what's the head loss between two layers of sand, between two pipes, like between these two pipes, or between two that are adjacent, I guess. And between two that are adjacent, there's 20 centimeters of height between them, but there's not 20 centimeters of settled sand when the sand is fluidized. There's 20 centimeters of fluidized sand. And so the actual amount of sand is less. So let's figure out how much equivalent settled sand would be in there. So we have this relationship between the height of the filter sand during backwash and when you're in filtration mode. So we can solve for the height of filter sand, given that we know the height of the filter sand that's being backwashed between two layers is 20 centimeters. So HFI sand, that's the settled depth of sand. This height of filter sand that's in backwash mode and is fluidized is actually 20 centimeters. And the result is that there's 15 centimeters equivalent of settled sand in between two pipes when it's fluidized in backwash mode. So this is the head loss per 20 centimeters of expanded bed. So going back to this slide, the distance between this water level and this water level, distance between two adjacent manometers should be roughly 15 centimeters if the filter is expanded. I showed a graph like this, whatever, a week ago, except it looked different. So in this case, what I've changed is that instead of being the total head loss through the sand, which is what I did the last time, this time I'm saying I'm measuring between two fixed locations in the sand bed, and I want to know what the head loss is over that fixed length. And so it starts out the same because initially the bed isn't fluidized. And so we get the same linear relationship where the head loss through that chunk of sand keeps on increasing linearly according to the Kármán-Kozsány equation or the Ergun equation. And then when we get to 1, which means that the head loss is equal to the height that I'm interested in, when I get to 1, that's just enough to fluidize it. I didn't specify on this slide, but I should have. I'm talking about silica sand, okay? So that's at 1, it's just enough to fluidize it. And then as we keep increasing the velocity up through the sand expands more and more, and there's less and less sand in between my two measuring points. And so that the head loss drops again. So this is kind of a strange relationship. And to be full disclosure, I actually don't have any clear insight about what the shape of this second line is. It's probably not a line. It's got to have some curvature in it, but I don't know how it curves. So the first part of the line, I'm confident in that because that's the Kármán-Kozsány equation. It says it's linear. The second part, I'm not sure what's happening. And it's got to be a function of the size distribution of the sand, because this is showing sand slowly becoming more and more dilute. And when we get down to 0 head loss, that's because we washed all the sand out. And all the sand is gone from your filter, and the plant operators are yelling at you and they're asking you why you did this. And you, in turn, are yelling at Agua Clara Reach for designing a filter that it was possible to do this to. Oh, did you see that line of excuses that we just threw out there? Because if it shouldn't be possible to dump all the sand out of the filter by doing something that just blows all the sand out the top of the filter. The filter should have some safeties built in it, so you can't do that. That's why Agua Clara Reach should take some responsibility for making sure that you can't dump all your sand by mistake. So now we're in filtration mode, and we're just beginning filtration. And what we see is that the water level in the inlet box is now higher than any of the pipe stubs. And so water is getting into each of the inlets. Water in the outlet box is coming in and then flowing out, perhaps over some weir or something, to get to where it's going to go to the distribution tank for people to drink eventually. The water level in the outlet box is very, very similar to the water level inside the filter box. You see that? And it makes sense. Let's follow the pipe that makes it clear that those pressures need to be, or those water levels need to be almost the same. If we go in the top inlet, that's this one right here, go in the top inlet, and we find out that we're just at the very surface of the sand bed. And there might be, well, there's no water really flowing into this top, because all the water is flowing down through the sand to go out this outlet. And so that means that this water in the filter is a measure of the pressure at the end of this inlet pipe. And so if these two water levels are different, the only reason they can be different is because there's a little bit of head loss in this inlet pipe, or perhaps more accurately, in the orifices that are in the branches that are letting the water out into the filter bed. So this little difference is because of the head loss through those orifices that are letting the water into the sand bed. What else do we see here? We see the same relationship that I talked about like 15 minutes ago, that the difference between the water surface in the filter bed and the water surface in the siphon, that H is the same at both ends of the siphon. See that? Here's H equals rho air over rho G, and same H at the bottom here, that H is rho air over rho G. Sorry, the pressure of air divided by rho G. I didn't mean to say rho air, I meant to say pressure of air divided by rho G. And the pressure of air, I feel like I did something wrong there. No, that's right, that's fine. Because that's giving you the pressure inside the siphon pipe, which is rho air, sorry, which is the pressure of air. And that's constant because the density of air is small. So this is the pressure of air is constant inside that pipe. During the filtration cycle, during filtration, the water level in the entrance tank slowly rises. The water level in the filter box slowly rises. At some point, you get to a maximum value where there starts to be overflow, and that indicates that it's the end of your filter run. And I don't know if I'm up to answering this question or not. I have this question here: what causes water to flow through the filter bed? Like, when you look at this, does it seem to you like maybe more of the water ought to flow in the bottom layer of the filter than in the top layer of the filter? Or Like, does it seem like they should be different? Or maybe backwards from what I said? Like, can you imagine that each filter layer would get the same amount of water flowing through it? Or does it seem like there's no way that will work? Ooh. Take any filter layer and follow the path of water going in and water coming back out. What do you find? Which filter layer shall we take? Let's take the bottom one so that it's perfectly clear. We'll take the bottom one. Water going in comes from the inlet tank. The water level is this high in the inlet tank. Water goes in, goes through the sand, goes up to this outlet pipe, and the water level is this high. That difference in water level is what's pushing the water both through the pipes and through the sand in that layer. And that's the same difference for each layer. So as long as my losses in my pipes are relatively small, each layer is going to get the same pressure difference pushing water through it. Do you buy that? Even though these layers are at different heights, they each have the same potential energy difference that's pushing water through it. I might need to come back to this because I really should have drawn some more stuff on the board, but I didn't. So it's powered by differences in piezometric head, and I'm realizing I didn't define piezometric head nicely for you. Piezometric head difference is the same as the difference in water level between those two tanks. So maybe you believe that. And I feel like, let's just take a look at a couple pictures. So looking at the controls and the controls are in a bad shape right here. This is not normal filtration operation. I can tell you that because this is the inlet box and it's overflowing. And they've got all these plugged, which means that they're actually operating this in bypass mode right now. And I don't know why, and I don't like that. Looking inside the bottom, like they call it the basement, it's the pipe gallery. And this is in construction mode. So not all the pipes are installed yet. And you can begin to imagine that it's a lot of work installing all of these pipes in the pipe gallery. I think I will end today with this, which is one more piece on thinking about the design. And so I've taken a chunk of a filter and I'm showing the sand and then inlet pipes and outlet pipes. So inlet pipes, outlet pipes, inlet, outlet, inlet, outlet, inlet, and showing the water flowing through each of those layers. And then I want you to imagine, wait, what is the water doing between two layers? And so I've zoomed in on 4 of those pipes and I've drawn, just without doing any math, I've just drawn conceptually what the streamlines must be doing. So the streamlines are coming out and they show that the shortest path is coming out of an inlet pipe and into the top of an outlet pipe. That's the shortest path. And the longer path is to go through sand that's further away. And what that means is that the further we space these pipes apart horizontally, the worse it gets. You see that? Because we would like there to be uniform flow vertically in the sand bed, and we would get that if the inlet pipes and the outlet pipes were right against each other. But if we did that, we can't backwash the sand, right? We need to be able to have a way for water to go up through this whole thing and fluidize the sand bed. So we can't have the pipes right next to each other. So we separate them, but not by a whole lot. And we make sure that the separation distance is still small compared with the height of the layer, so that it at least distributes reasonably well. And we have not done any research on that. This was just like back of the envelope, draw a picture and say, this ought to be reasonable. We know what factor is important, but we've never done any calculations on that. So that's this constraint. Horizontal spacing between inlet pipes or outlet pipes must be small compared with the layer depth. And another constraint, all the inlet and outlets must be high and dry during backwash so that they get shut off.